before we start, let me tell you something about the exercises that we will be making. Apart from the theory, we will do a lot of numerical exercises during this course. It will be very interactive in the sense that it works like this. I give you the text of the exercise, and then you have, say, 10 minutes, 5 to 10 minutes to solve it. Obviously, you can solve it by yourself, you can solve it with your compañeros and so please bring with you your scientific calculator, because you will need it. Obviously, if you don't want to do exercises, you can sleep on the table. It's perfectly fine with me. But I think it's very useful to prepare in preparation of the exercise. We will start with exercises on Friday. So today and tomorrow we'll put some more theory that we need, and then we start doing exercises as well as theory. Okay. We were talking about bands. Let me make a drawing that sum up the propagation modes. Just for your reference. We have the ionospheric wave, or we have the ground waves. Or we have something that we have not talked about, that is the tropospheric wave. The ground waves then can be classified into different types. That is the so-called space waves. Do not confuse space wave with sky waves, and they are different things. And surface waves. And then space waves are the one we are interested into, because are direct waves, and then reflected or diffracted. So this is typical of very low frequencies. This is, so let me say, we talked about this yesterday, but this is typically very low frequencies, medium frequency. This is mainly medium frequency, high frequencies. And those waves here are what we are interested into. VHF, UHF, and microwave. Okay, so we will focus on those propagation mechanisms. What we will see now. As I said last time, first of all, antennas. some basic parameters of the antenna. We will not go into the electromagnetic theory. It's useless for our application. Then we will start looking at the propagation itself. Following this logic, first of all, free space. What is the signal that we receive in free space? The equation is the so-called freeze equation. Called also link budget. Link budget because you can actually make a budget, a power budget of the radio link. So this will be our reference. But it's really just a reference because we'll discover that we are not in free space. Why we are not in free space? What is something that is always present on this planet, wherever you are? Here, the terrain, the ground. You can get rid of it. So the next thing that we will see is the effect of ground. Ground means anything, including water, fresh water or sea water. Now, the effect of ground are different. Okay, we start looking at the reflection coefficient of the Earth. Reflection coefficient of the Earth, it depends on the nature of the ground. And it's very different when you go from water to conductive ground to sand, rock, very different. Reflection we will investigate what happens when your electromagnetic waves hits at what we call a flat surface. And flat is a relative word. We will discover. Next step is to see what happens when you have a reflection from a rough surface. We will discover that flat or rough depend on the wavelength. It will depend on the frequency. In particular, a flat surface will give rise to what we call specular reflection. And a rough surface will give rise to what we call diffuse reflection. So that's reflection mainly. But what is also always present on this planet, beside the ground?
Meaning?
yes, but not everywhere.
Building.
Not everywhere.
Air.
You breathe the atmosphere.
Ah.
In particular, we will be focusing on the lower layers of the atmosphere that is called the troposphere. The effect of the troposphere is extremely important. In particular, we will see it gives rise to refraction. That is, the electromagnetic wave in the troposphere, in our planet, in any planet that has got an atmosphere, really, never travels along a straight line. Never. It's always bending. And the bending of the electromagnetic ray depends on the status of the atmosphere. And you have to take into account this curvature when you design a radio link that is, whose length is, say, more than 20 or 30 kilometers. Okay, so this is the typical problem that you find in microwave links. And eventually, someone said buildings, yes. Since you can have urban environment or hilly environment, you can find your you can be propagating over what we call irregular terrain. And this includes buildings. The effect of this is diffraction. And this is a very important propagation mechanism when you are, for example, in a urban environment. Reflection and diffraction are the main propagation mechanisms when you are in that kind of environment. So this is our schedule for today. Well, no, sorry, for today. We won't be doing everything today. We start with antennas. And then we go through all those topics in the next days. Antennas. What is an antenna? One of the possible definitions of antennas is transducers. A transducer is a device that converts one form of energy into another. For example, if you take a microphone and speak into the microphone is a transducer because it converts the mechanical energy of the pressure waves into electrical signals. The loudspeaker is a transducer because it does the opposite conversion. It converts electrical energy into mechanical energy. So antennas are transducers, and what do they convert? They convert guided electromagnetic waves. The electromagnetic waves travel along transmission lines, coaxial cables, waveguides, etc., into radiated electromagnetic waves. And this is not a simple task. The antennas are not trivial. And usually they work very well both ways. Same antenna, same device converts electromagnetic energy from one type in another one. In other words, antennas can work this way, and that's what we call transmitting antennas. Or they can work this way, and this is what we call receiving antennas. But they are the same object. Please take in mind, because this is important, the antennas are passive devices. They cannot create energy. They can radiate at most the energy that you give them. So you have to understand the meaning of one important parameter, that is the gain of the antennas, la ganancia dell'antenna. It's very different from the gain of an amplifier. Because an amplifier is an active device. The antenna is a passive device. So that gain will be clear in a moment, has a complete different meaning. Okay. What are the parameters of the antennas? Okay, let's start with an antenna that I depict like a blob. So no particular shape, just a blob. So those are the terminals where the circuit is connected. So you can define here the voltage and the current entering the antenna. This is the port of the antenna. The guided electromagnetic energy enters here, and then it is radiated from the antenna, or the other way around. Let's start with an antenna, with a very particular antenna. It is a reference antenna, the so-called isotropic antenna. The isotropic antenna isotropic means that it radiates in the same way in all directions. Radiates uniformly regardless of the direction. This antenna does not exist. It's not possible to build an isotropic antenna. It's not possible to build an antenna that radiates in the same way in all directions. But and nevertheless, we consider this as a reference. So, let's assume that this is our isotropic antenna. Now, well, I'll do another one. Let's assume that the transmitter or the circuit is providing a total power of PT watt. And let's assume also that the hypothesis that the antenna is lossless. That is, it radiates perfectly 100% of the energy that you give to the antenna. You give to the antenna 10 watt, it radiates 10 watt completely. So this is what we call ideal antenna. Now we ask ourselves, what is, let's imagine that I am an observer in a point P at distance r from the antenna. What is the power density in that point? Remember, we call the power density the Poynting vector S. And we call this, the power density piece is, we call it SI. That means for incident, the I stands for incident power density. Okay, we can demonstrate that, and it's very easy to verify, that the power density here at distance r from the antenna is simply power that you put into the antenna divided this quantity. There is no dependence on the angle because the antenna is isotropic. So there is only a dependence on the distance. And this is a pure geometrical factor. The explanation is this. If you think if this is the center of the antenna, what happens when you go from R to 2R? It happens that this area here is proportional to R squared. So this area here is proportional and since in this cone the total power is constant, the power is spread over an area that is increasing with the R squared. So this dependence is simply due to the fact that the further away you go from the antenna, the larger the area where the power is spread. So it's a pure geometrical spreading mechanism. There is nothing electromagnetic in it. We can verify that this equation is in fact correct because let's calculate this. Those are simple calculations. Let's calculate what is the total power that crosses a sphere, a spherical surface of radius r. How do you calculate the total? You sum up all the contributions. Mathematically, this summation is an integral. When you calculate an integral, you are doing a summation. So, if you calculate the integral over a spherical surface of this quantity, this is a surface integral, so you have here yes. What do you get? Okay, you can put all those are constants, so you know they can be taken out of the integral sign. The elemental area the elemental area ds is equal to r squared. This is the elemental area, is r squared multiplied the solid angle d omega. So you can replace this thing with 1 over r squared. Instead of putting the s, you put r squared ds, the omega. Those simplify themselves. And the integral of the omega of the elemental solid angle over the solid angle, you know what it is, maybe, is 4. So eventually you find that the total power across the sphere of radius r is the power that you have been radiating. This means that the power is not lost when it propagates in space. In other words, the signal, if we are talking about the radio signal, the signal is getting weaker and weaker and weaker when you go away. Not because the energy is disappearing, because the energy is constant, but just because the energy is spread over a surface that is getting bigger and bigger and bigger. And this is something that you cannot eliminate. We will see that this phenomenon is called free space attenuation, but it's not really an attenuation. It's just a spread of the energy over a bigger and bigger surface. Those waves that are going away from the antenna, which kind of waves are? They are not plane waves, but are spherical waves. Plane wave does not exist, as I said. What exists in nature are spherical waves. Why did we talk about plane waves yesterday? Because if you are very far from the antenna and you just look at a small area, in this small area, that is the area of your interest, you can assume the spherical wave to be locally plane. Okay, we know it's not plane, but if you don't move too much from that point, around that point, the wave can be considered to be plane. So you can apply all the things that we know for plane waves that are more easier than spherical waves. Okay, that's the isotropic antenna. As I said, there are no antennas that are isotropic. You cannot build isotropic antennas. It would be nice for some application, but it cannot be done. So what changes in real life? Actual antennas are not isotropic. That is, they concentrate the energy in one or more directions with respect to other directions. Just to make an example that what is clearer maybe. The isotropic antenna, you can think of the isotropic antenna like the old lamp, bulb lamp, lampadina, that illuminates any direction in the same way, roughly. That's the isotropic antenna. That it does not exist. What any antenna behaves like is like the headlights of your car. When you put that lamp in the headlights of your car, you have a direction where the energy is concentrated and directions where the energy is removed from. Because we have to remember that the antennas are passive devices. So if they concentrate the energy in a given direction, they remove the energy from other directions. What changes in our equations? Not much. Apart from the fact that now the power density depends on the direction. Those two angles, theta and phi, are the typical angles of a polar coordinate system. It's quite important that you get familiar with the polar coordinate system because it's the natural coordinate system for antennas. Not the Cartesian rectangle, but the polar. For your convenience, I remember, let me remind you that in a three-dimensional space, where those are the classical axes, the polar coordinates, if you have a point P, the polar coordinates are the distance r from the origin, the so-called co-elevation angle, theta, co-elevation. The elevation is the angle from the horizontal plane. And the azimuthal angle, that is the angle between the x-axis and the projection on the xy plane. This is the projection on the xy plane of R. That's the polar coordinate system that we will be using. So what changes in the power density? Not much. but we add something to the isotropic expression. Two parameters, a constant d and the function f of theta and t. And we will discuss those two parameters now. Now, d is what we call directivity of the antenna. It's not the gain, no es la ganancia. It's very close to the gain, hopefully, but it's not the antenna gain. It's called directivity. And this function is called directivity function. Okay. Directivity function simply tells you, no, now let me add something. The directivity function is defined in a special way. It's a function that is normalized to 1, and its values are between 0 and 1. This notation means that it is always somewhere in some direction for some values of theta and t is equal to 1. And it may or may not be 0. For sure, in some direction is equal to 1, but it may not go down to 0. But it's between 0 and 1. This function describes the way in which the antenna radiates in space. As I said, there is one or more directions of maximum radiation. This is normal. Somewhere there must be a maximum, one or more maximum. And are the values where particular directions identified by specific values of theta and t, where the directivity function is equal to 1. Okay, let's consider that direction. The direction where the antenna is radiating at best. What happens? Maximum value of the power density will be the transmitted power divided by this times d. D is, we will see, is a number that is always greater or equal to 1. If we think about the isotropic antenna that we have seen before, if you fit the isotropic antenna with the same power, that's the density that you get. So from this, if you divide those two equations, you find very easily the definition of directivity. The directivity is simply the ratio between the maximum density of your antenna divided by the density of the isotropic antenna. And since this parameter is always greater or equal to 1, then you find that for lossless antennas, we are always talking about lossless antennas so far. The maximum power density will be greater or equal than the isotropic power density. What is happening simply is that the antenna is concentrating the energy in a given direction. This concentration must be done at the expenses of the radiation in other directions. The total power, the total radiated power must always be constant, must be Vt. So there must be a relation between those two parameters. There must be a relation between the way the antenna radiates in space and the value of the directivity of this, of how stronger is the field. You can, in principle, you can imagine that the narrower, the more concentrated is the radiation in a given direction, the larger will be the directivity. That is, the higher will be the power density with respect to the isotope. Taking this into account, we will now derive a very important relation between those two parameters that is fundamental for the antenna theory. Let's start from this. And let's calculate again the total radiated power. That is, let's calculate the integral over our spherical surface of this time the expression is a little bit more complicated because T divided 4πr squared and if we, as usual, take the constants out of the integration sign, we end up and we replace the S as usual with R squared the omega. We end up with something like this. And this the total radiated power must be the transmitted power, since we are not losing power. By comparing this equation, you find that the directivity is perfectly related to the directivity function through this equation. And this is a fundamental relation that we will use in some exercises to calculate the directivity of one antenna when we know the way it radiates. You will have to do some integration, but nothing particularly complicated. Okay, questions so far? One thing that I didn't mention, because it's going to be too complicated, is that every antenna radiates an electromagnetic wave with a given polarization state. So the radiated field has a very precise polarization. Depends on the way the antenna is built. We just have to keep this in mind when we are going to make a radio link. But we will go back on this further. There was a question?
I have a question about the G parameter. It's the same, the G parameter is the same of the fundamental or is different?
Say it again. Sorry, your question is the same or?
The G parameter is the same in electromagnetic wave or not correlation?
No, it's different. No, oh yes, you're talking about displacement. No, it's a completely different. No, it's not the displacement. In fact, it's a constant, it's not a vector. We will often find parameters that have been used in different aspects of electromagnetic fields. It's quite confusing. It's not the same. Okay. Other questions? Okay. So when you want to specify or buy an antenna, what parameters you specify? Okay, one parameter that we have seen so far is the directivity function. So when you look at a specification, or you go through a catalog, or you want to buy an antenna, you have to know the directivity function that you want to have. A common mistake that is made when you think about the antennas is, when you think that you want to buy an antenna, you say, okay, I want to buy the antenna with the highest gain. This is wrong. Because we have seen that, we are not seeing the gain yet, but the directivity, it depends on the directivity function. So when you have to choose the antenna that you want, don't think about the gain. You have to think about the directivity function. You have to think about the way you want the antenna to radiate. And the gain is what you can get. You cannot have gain and directivity function that you want, because the two things are strictly related to that precise equation. Let me be more precise. if you want to set up a broadcasting station on FM and TV station, maybe you want to cover all the users around you. Then you need an omnidirectional antenna. Omnidirectional is not isotropic. Omnidirectional, I will show you, but means that radiates in the same way on the horizontal plane, on the azimuthal plane. If you want to set up a microwave link from point A to point B, you may want a directive antenna to reduce the interference. So you have to choose exactly the directivity function first, with your application in mind. Then obviously polarization. Polarization, we will see, depends also on the application. Okay, what next? No antenna is ideal. No antenna is lossless. You can have losses in the conductors, and you can have losses in the dielectrics that make the antenna. Depends on the frequency. It's not always the culprit is not always the conductor. You can have strong losses also in the dielectrics. But the story is you always have losses. How do we express those losses? Through a parameter that is called antenna efficiency. And you indicate it with the parameter eta. Oh, being an efficiency, by definition of efficiency, is something that is